Okay, hi. My name is Giuseppe, and yeah, exploring brain dynamics using DySCo. So this talk is going to be about DySCo, which is a recent framework for dynamic functional connectivity. So it's mostly a methodological talk about this new toolbox. However, hopefully by the end of the talk, I will develop also theoretical considerations about brain modes and why they are cool, but probably you already think they are cool, otherwise you wouldn't be here anyhow. So yeah, let's start with this. So the goals will be, first of all, I will explain what is dynamic functional connectivity, why I think it's important, and what is DySCo. Secondly, I will explain how DySCo works, and finally, I will show some applications. So let's start. What is dynamic functional connectivity and what is DySCo? So good news, we have two important slides, this one and the next one. Then all the rest is just going from these two key concepts. So you just have to be attentive now. So what is dynamic functional connectivity and why it is an interesting tool to understand brain dynamics? So, okay, you are all familiar with static functional connectivity. So, you know, classic matrix where every entry is a correlation or any other measure or of statistical interaction between brain regions. And you may be familiar with the fact that recently people are starting to do it dynamically. So to study how this changes in time, how connectivity evolves in time. Now, I think that dynamic functional connectivity is a great tool to understand brain dynamics, and in particular, the switch between brain states. Let's do this toy example where we have only 3 brain regions. And in this toy example, you have a first part where the first 2 signals are highly correlated, and the second part where the first and the third signals are highly correlated. So the brain is kind of switching between these 2 spatiotemporal patterns of interaction. You can see this as a matrix, a correlation matrix. You can see it as a graph, or you can see this same phenomenon as a high-dimensional, in this case, 3-dimensional. In reality, it can be 10,000 dimensional, a high-dimensional cloud of points having a specific shape and exploring a specific spatiotemporal axis of variation. And this would be, let's say, the PCA interpretation of this. And in this example, this toy brain is switching between this blue and this green brain states. However, if you do a static functional connectivity, you kind of get these spurious things that are not actually reflecting what's really happening with the signals here. So I hope I convince you with these first slides that dynamic functional connectivity is not just a matrix that changes in time, but it's a way to understand how brain states evolve in time. Second important slide, what is DySCo? So DySCo is a general framework for dynamic functional connectivity, which addresses 3 main limitations of the field. The first limitation is that there are too many approaches. Like over the years, a lot of different things have been proposed for dynamic and also in general for functional connectivity. Sliding window approaches, sliding window correlation, phase locking approaches, wavelets, co-fluctuation, and so on. So, you know, it's a mess. Second limitation, high dimensionality. We know fMRI signals, unparcellated fMRI signals are very high dimensional, or this is an example of neuropixel in monkeys, so high dimensional electrophysiology. Let me give you a practical example. Imagine you have a finer parcellation. So rather than the typical 100 parcellation, you have, I don't know, 1,000 brain areas. You start having, or, you know, voxel-wise, so tens of thousands of voxel. Your matrices, which are dynamic, so you have many of them, may become huge with billions of elements inside. So you need a fast and compact way of working with them. Once you have these matrices, what do you do with them? And over the years, a lot of different approaches have been proposed. For example, clustering, the FCD matrix, which is a distance matrix. I'm gonna explain this in the application part. The reconfiguration speed, which is like the speed of the evolution of this matrix in time, the entropy, metastability, and so on. Okay, so DySCo is a unified mathematical framework that works for all these approaches, first point. Second point, it uses a unified and optimized EVD to address this high dimensionality problem in an efficient way. And finally, it proposes a unified set of measures. And by combining these measures, you can do all the analysis I'm mentioning here. And these measures are very simple linear algebra measures, which are norm, distance, and entropy. So yeah, this is it. I explained what is dynamic functional activity and what is DySCo. So this was the important part of the talk. So now how it works. So I will explain in 3 slides the unified mathematical framework, the EVD, and the unified measures. So I'm happy to discuss more the maths. There's not going to be time now for the maths, but the idea is that all these matrices and even more like a general class of matrices that have this form where this F function is can be a lot of well-behaving functions. Well, all of these matrices, you can always find a linear or non-linear mapping such that you can always write them in this form. So in a sum over a window of x transpose, where x is the signal vector, or a linear or non-linear transformation of the signal vector times some weights. And this is trivial, for example, for a correlation or for a covariance matrix. Is non-trivial for a lot of other approaches. And to give you a graphical intuition of this concept, the idea is that you can always find a space, even with phase locking, for example, and I'm happy to discuss this in the theory later. You can always find a space where your problems become this idea of the clouds of points and the geometry evolving in time. Okay, so unified mathematical framework. Optimize EVD. Once we claim that we can put all these measures in a unique framework, we can do an optimized EVD, which is a temporal covariance EVD, which has been used a lot in other fields, to compute eigenvectors and values of the matrices in an optimized way. And again, the intuition here is that signals in the window typically are high dimensional in space, but low dimensional in time. So you can use the low dimensionality in time to optimize computations. And this efficient and lossless representation in terms of eigenvalues and vectors is very efficient, both from a time perspective, so how to compute the matrices. It becomes orders of magnitude faster, for example, for voxel-wise fMRI or a high-dimensional electrophysiology, but also efficient from the memory consumption, so the memory to save the matrices. Okay, finally, unified measures. So the mathematical part explains that if you take the matrix norm, which this is a non very mathematically wise way of expressing what the norm is, anyhow, it's just graphical intuition, the distance, which is the similarity between two matrices, and the entropy, which is the dimensionality of these matrices or the cloud of points. If you combine these measures, and we also have the combined measures that combine them, you can do a lot of DFC analysis. And I will show this later in the application. And the key here is that all these measures we rewrote the measures in the compact EVD space. So the idea is that you are measuring all these things about the matrices, but you never expand the matrices. You never unpack them. They all work in this compact space. And again, this can be extremely beneficial for memory consumption or time. For example, if you do a classical functional connectivity analysis, which is the fingerprinting that we have heard before about fingerprinting, using DySCo, it becomes extremely faster because you are using these measures that work on top of the optimized EVD. Okay, so to summarize, DySCo is a framework for dynamic functional connectivity that works with this optimized EVD, and it proposes these measures to do dynamic functional connectivity analysis. Yeah, and I work with Rob Leach, and it was very working with Rob Beach is always a pleasure because he does these amazing animations, and this is a brain map that turns into a DySCo ball. So we have a graphical user interface for the DySCo toolbox, and if you use the graphical user interface, this is going to be the opener of the interface. So just two side notes, DySCo works also with static functional connectivity, because static is just dynamic in a bigger window. And the idea of being unified is not only mathematical, but it's also about working with multiple types of data from electrophysiology to imaging. And yeah. So, okay, what is DySCo? How it works? Finally, I'm going to show you some applications. So, yeah, first task fMRI data from the HCP dataset, very famous project where you have a subject doing the task inside the scanner. And in particular here, we are interested at the switch between the task, rest, task, rest, task, rest. And again, the idea here is that we are working with dynamic matrices, which every matrix has billions of elements inside. So you cannot do this with classic, let's say, approaches where you unpack the matrices. The first measure we show here is the reconfiguration speed. So the distance of matrix at time t and matrix at time t-1. So basically it's the speed of the evolution of these matrices or clouds of point. And you can see these peaks corresponding to the switch between task and rest, sorry, rest and tasks. And also the entropy is correlated to the task structure. Very interesting. And again, I want to highlight again this idea of high dimensionality. Also, the functional connectivity dynamics matrix. This is a time-to-time distance matrix. So this is all the possible distances of all the possible time points. And again, you see it reveals this tiled structure, which is the tiled structure of the task. Again, I was saying the point here is that we are studying these axes of variation and how they move in time. And indeed, you can see that, you know, the axis of variation. So this is kind of the representation of the matrix through the main eigenvectors in task, in rest, task, rest. And you can see basically here the implementation of this concept here. So you can see the switch between these two different spatiotemporal patterns of variations. Okay, so this was the first application. Very briefly, I don't think I have a lot of time. To give you another example of how DySCo allows you to track dynamically the effect of connectivity in time, here we applied it to pharmacological MRI. So we had rats, and ketamine was injected during the scanning. And if you look here, you can see that after the injection of ketamine, you see that with DySCo we can kind of real-time track the effect of ketamine on the global connectivity, so on the total amount of connectivity. Just to give you another example application. So this is it. DySCo is a tool to understand brain state dynamics using this eigenvector slash matrix view. And so this was DySCo. Now I'm going to give you kind of a teaser for another project. And the idea here is that you could ask me, okay, but these matrices, are they causal or not? And the answer is no, they are not causal. All these interactions are not causal interaction. And so I started this experimental effort where we instead did optogenetic perturbation. So we have wide field calcium imaging here of mice, and we can do optogenetic inhibition, and we can target brain areas. So basically you can target any of these brain area and measure the effect of the inhibition on all the other areas. So you can build a cortical mapping of connectivity. You can do a cortical mapping of what happens to all the brain when I stimulate one of these areas. And you can summarize these results in the cortical perturbome as defined by Sada and Klopath, which basically is that previous image, but in a matrix. And we know that correlation is not causation, and indeed this thing here is very different from this. I'm using a different color palette because the unit of measurement of this is delta F over F. This is correlation, so it wouldn't be fair to use the same color palette. So to conclude, okay, we know that correlation is not causation, so does it mean that we have to throw functional connectivity away in the bin? And my personal understanding is no, because functional connectivity is still the signature of a dynamical system evolving in time and visiting different dynamical states. So exploring a high dimension geometry in time. And to conclude, this eigenvector approach is not only a trick for making computation faster. These eigenvectors are the intrinsic nature of functional connectivity. Like, I like to see FC as a bunch of eigenvectors, a bunch of axes expressing how the signal evolves in time. So brain modes here are not only a way to make computation faster, also the intrinsic nature of DySCo. And to conclude, if you are interested, we have a toolbox available both in MATLAB and Python. We have also the graphical user interface and the nice animation I was showing before. And there's also a rock band that in the 80s dedicated a song to our method. And also recently an Italian song. So yeah, we also have songs dedicated to the method. And with this, I thank you very much. And thank you also to the amazing collaborators I've been working with.